Okay, great. So indeed, so today my talk is entitled Complexity, Quantum Mechanics, and the Structure of Space-Time. And actually, the way this talk is going to go is I'm going to start with the structure of space-time, go backward through quantum mechanics and complexity, and then go back forward through quantum mechanics and the structure of space-time. So it's going to kind of do a loop through this. So the story starts here with general relativity, which is Einstein's theory of space and time. And Einstein taught us more than 100 years ago now that matter and energy can warp space and time. So this is like this. If I draw a picture of the fabric of space like this, think about it as a piece of cloth, if you will, you put some matter in it that's supposed to be our sun. It just bends the space, and straight lines become bendy, and that kind of thing happens. The really unusual thing about general relativity is it says that time is bent, and that's a very hard thing to visualize, right? The bending of time has many strange effects. For example, it's true that your head ages faster than your feet. It's also true that the light emitted from a distant star looks redder to us than when it was emitted. And all these strange things are happening essentially because of an effect of the warping of time. And in fact, if space and time are sufficiently warped, the fact that you have to move slower than the speed of light implies that something called a space-time horizon can exist. What's a horizon? It's a kind of locus, a place in space and time, where if you go past the horizon, you can't go back. You can think about it like this. If this axis is space and this is time, and I've drawn a little cylinder, what I'm drawing here are little cones in space and time, where if I start here, these are the directions, the upper part of the cone, are the directions into the future that, since time runs upward here, that I can follow if I'm moving slower than the speed of light. And back here are the places I could have come from slower than the speed of light. So it's possible in general relativity for these cones describing directions you can go in space and time to tip over in such a manner that they point inward past this line, and that's what's called a horizon, right? It's a place beyond which time is flowing in such a way you can't get back out. Now, this has a consequence. So back already about 100 years ago, a consequence of this kind of thing that was demonstrated by Kurt Schwarzschild, he didn't understand it in these terms, but he displayed a solution to the equations of general relativity that we now call a black hole. And 40 years later or so, Finkelstein showed that this thing that Schwarzschild had written down had the property that there was a horizon. If you went past it, you couldn't come back out and get back out to the boundary, the infinity of space-time. Still more time passed, and then Kruskal showed that this weird solution that Schwarzschild had written down to the equations of general relativity was a wormhole that connected two distinct universes. One universe, another universe, and there's a pathway between it. Although sadly, it's a wormhole that has the character that it sort of appears and kind of pinches off, so you can't actually go through it, more's the pity, to go between two universes. Still more time passed, and the 1960s and 1970s, Stephen Hawking and Roger Penrose proved what are now known as the singularity theorems, which basically show that if you take any sufficiently heavy star, allow it to burn out its fuel, its nuclear fuel, it will collapse, and eventually when it collapses, it makes a black hole. So people draw, these things are very hard to visualize, so people draw all kinds of diagrams to try to visualize this. So here's a picture like this. So what you have is this the past infinity, where things come from. Here's a future infinity where things go to. And people draw these sort of conceptual diagrams where in this picture, time runs up, space runs this way. And there's this region of space where if you go inside here, you're unable to get back out into the future of the universe. Instead, if you go forward, you hit the singularity. This is actually a technical thing called a Penrose diagram. But for us, it's a picture capturing the concept of the idea that once you go past this dashed line, the horizon, you're unable to get back out. So this region in the middle is kind of causally disconnected from the rest of the universe. Causally disconnected means once you're in there, there's nothing you can do to serve as a cause for things happening outside. So this has a meaning in terms of the information in the universe. You could take a thing that contains information, right, and a hard drive if you wish. You could put it behind the horizon, and according to this picture, it cannot come out, and therefore you've hidden it. It isn't erased, mind you, so far in this picture. It's just hidden behind this horizon. The universe may still know the information, but it's hidden forever from the outside. So I should say that this is all very strange, and so you might wonder, is this just a fiction? But actually, black holes do exist. While they were predicted originally just as a piece of mathematical physics, well, when I was a kid, there was one candidate. It was called Cygnus X1. It was an X-ray source in the sky, observed in 1964. But by now, we know hundreds and hundreds of candidates. There's a black hole in the center of our galaxy. The Large Interferometric Gravitational Observatory has detected the gravitational waves, mergers of black holes. And this is even a picture of stuff spiraling into a black hole taken by the Event Horizon Telescope. So we definitely know these things exist in our world. Now, in the 1970s, there was another very curious development in theoretical physics. So this is a bit of a technical slide, so I'm going to talk you through this. So this is an audience which is very sophisticated. So all of you have heard of the laws of thermodynamics. Thermodynamics are the laws in physics that govern how heat works, how entropy works, things of this kind. Disorder, energy, temperatures, things of this kind. And famously, there are three laws of thermodynamics that were established already in the 19th century by the greats of the 19th century. The first law says that if you heat a system, right, and it has a temperature T, well, the change in energy in the system is related to the temperature T and the change in its entropy. So there's a relationship in how much disorder or entropy you add into a system and how much its energy changes. That's a sort of universal rule that has to be satisfied by physical systems. There's a second physical rule that universally the entropy or disorder in a system can never decrease. It's always non-decreasing. And then there's a third rule that says that in bodies that are in equilibrium, the temperatures are constant. So in the 1970s, Bardeen, Carter, Hawking, and Bekenstein did a set of Gedanken experiments, thought experiments, in which they would imagine stuff like lowering stuff towards a black hole, trying to reel it back up, things of this kind. There's mental experiments of different kinds, and concluded that black holes also satisfied certain laws of the following kind. The mass of a black hole, if you increase it, the area of its horizon increases according to a certain equation. Turns out that in any classical process, the area of a black hole can never decrease. It can only increase. That's because stuff falls in and can't get out. But this formalizes that. And then there's something else called the surface gravity that's constant over the black hole. So in these famous papers, these authors observed that there's an analogy between these sets of rules, one about black holes, the classical physics of black holes, and one about the laws of thermodynamics. And then they famously ended with a phrase saying, well, but you shouldn't take this too seriously, right? Because one is about black holes, one is about thermodynamics, and here this means that, if you were to take this seriously, the entropy always increasing means black holes must somehow erase information, and, in any case, if this analogy were true, well, this thing on the laws of thermodynamics concern bodies that have a temperature, have a heat. And anything that's warm radiates, right? It radiates a little bit of photons, radiates a bit of heat. So you should expect black holes should radiate, but they don't, right? That's classical objects. So here is that formal analogy. So it was asked in this paper, maybe you could somehow formally think about the area of the horizon of a black hole as somehow an entropy, but surely this is not possible, because if they were, it would radiate, and that can't be true, because all things fall into black holes and nothing ever escapes. I said that twice, because you would certainly think this is true, and this is where a series of paradoxes are going to arise. So enter quantum mechanics. So far, I've talked about, space-time and the structure of space-time, the physics of the first half of the century, of the previous century. At the same time that general relativity was being discovered and developed, at the same first half of the last century, quantum mechanics was being developed and discovered. Now, what does quantum mechanics say? So quantum mechanics, which a priori seems to have nothing to do with general relativity and gravity, says the following things. That first of all, the first statement is that microscopically, the world isn't classical, it's governed by quantum mechanics. So what does that mean? So look, so in classical physics, if, there's me and I'm going to throw a ball to Matt over there, I throw the ball and it follows a trajectory, and there's Newton's laws that tell me what the trajectory is, and it lands in Matt's hands. There is a given trajectory it follows. But in quantum mechanics, the rule, apparently, microscopically says that if I tell you that a ball went from A to B, then it has some probability, technically something called an amplitude, but anyway, a probability of taking any conceivable path from A to B. It could go to the moon and then go back down to Matt's hands, or it could go straight, it could do whatever it wanted. It's just that each of these things has a certain probability or amplitude, and they can interfere and cancel, and all kinds of things can happen. And the classical trajectory that we usually see is just the one that's most likely. Now, that is also a very strange concept. No stranger or no less strange than the warping of time by matter, according to general relativity. And if you want to have some sort of qualitative feeling for what this means, I would advise reading a story called The Garden of Forking Paths by Jorge Luis Borges. So this is a very beautiful story. And the final page of the story was the epigram to the PhD thesis of Hugh Everett, who invented the many worlds formulation of quantum mechanics that described this. So I would read that story. It will give you a very vivid sensation of what this idea is about. So amongst the other things that you learn from quantum mechanics is that energy can kind of change quantumly into other forms. Just like a thing can go from one place to another place through many different paths or different amplitudes. If I told you in my hand I have a joule of energy, the joule of energy can spontaneously fluctuate into anything else that has a joule of energy. It just has some chance of doing so. So for example, if you have energy in a gravitational field, it can spontaneously become a pair of an electron and a positron and then turn back into gravitational energy. That's an allowed process in quantum mechanics. And you know, there are so many, there's 100 years of experiments verifying in ample detail that this is all true. Right? It's just absolutely true. So this is all true. So in 1975, Hawking said, well, look, we have quantum mechanics and we've got classical gravity. Surely we should do both together because the universe has classical gravity and it has quantum mechanics. So he considered the following situation. So this is a picture of a black hole, artistically drawn horizon, these little dashes here. And you imagine that just outside the horizon, the energy in the gravitational field spontaneously fluctuates into a particle and an antiparticle. One of them falls in behind the horizon, and poor thing can't escape anymore. So you're left with a particle left alone now, and what can it do? It escapes off to infinity. So all of a sudden, because of quantum mechanics, because the microscopic nature of the universe is quantum, a black hole, which you would think classically can only grab stuff, cannot radiate stuff, instead radiates a particle. Even more amazingly, Hawking showed that at the level that you could do the calculation, at least at the time, this radiation looked precisely thermal with the temperature required to make this analogy between black holes and thermodynamics exact. That's an amazing thing. Amongst other things, it's amazing because it means that quantum black holes evaporate away if you don't keep feeding them. It's not true that they trap stuff forever, but there's a catch. The radiation, as I said, looks thermal. Thermal radiation is random radiation. Thermal radiation is as random as possible, consistent with the conservation of energy. There's no structure in it at all. So that's the kind of radiation that seems to come out of black holes. So that lands us on a paradox. Here's the paradox. I'm going to give you 3 versions of the paradox. Version 1 of the paradox is like this. You make a black hole from elephants or from dictionaries, and you put them into the, and there you go. The black hole is sitting there, it's in a box. There's no way to tell from outside what the black hole is made of, so you might say that the information is erased. Yes, so you might object, as this gentleman here said, saying, well, it's just hidden. It isn't erased. So then you go to version 2. You make 2 black holes of equal weight, one from collapsing elephants, the other from dictionaries, and you let them both evaporate. The radiation is thermal, and the temperature only depends on the mass and not on what the black hole was originally made of, whether it's elephants or dictionaries. So in the end, when the black hole's gone and evaporated, the information is erased. That's a better version, yes? So here's version 3. Let's make this even more stringent. I'm going to start the universe in a state of 0 entropy, no entropy at all. So that's called a pure quantum state. You're going to let the matter in this pure quantum state collapse to make a black hole, and then you collect the radiation in the box as it radiates, as it comes out. The entropy of the radiation, the disorder in the radiation, keeps increasing with time because, as I told you, the radiation is thermal. And if it's thermal, it means it looks random. And so you're collecting this random radiation. It's as disordered as possible. And so eventually the black hole is gone, and the entropy went from 0 to some very large amount. And so because you've increased the disorder, the information in the system was erased. So these are three versions of the statement that black holes, that putting quantum mechanics and black holes together causes you to have a paradox in this sense of losing information. So you might say, is that really a paradox? And it is. The reason it's a paradox is, well, the pillars of 20th century physics are general relativity and quantum mechanics. Here are some basic principles required for the self-consistency of quantum physics. First, quantum systems are described by the probability, more technically the amplitude, that they are in any given configuration. That's what I was describing earlier. Second, quantum systems can be uniquely evolved forward or backward in time to derive the probability of any configuration at any time. So if I tell you what is the state of a quantum system now, there is a deterministic rule that tells me the state for all future times and for all previous times. That has a consequence. The consequence is that in a precise sense, quantum systems do not erase information. It's not possible. It's a theorem. So now, we just argued that if you put general relativity and quantum mechanics together, you have information erasure. Something's just wrong. You can kick out quantum mechanics. You can kick out general relativity. You can kick out both. You modify both. Something has to give, because otherwise you have a problem with the edifice of physics. OK. So, well, so I'm a string theorist. And indeed, I started going into the field of string theory because of this paradox, because this seems so strange. And it's good to have paradoxes, because they give you pointed questions that you can try to answer. So the job of theorists is to imagine ways out of these problems. And a conservative answer to this problem is don't throw out quantum mechanics, don't throw out general relativity. Actually, there's some kind of secret argument for information recovery, and there's a reason why we couldn't see it before. So let's investigate that. So here's an argument for information recovery. So let's suppose that I have a black hole that is in some particular microstate, some microscopic configuration, that is determined by whatever originally made it. Right? That could be black holes, that could be elephants, that could be dictionaries, whatever it is that we used to make the black hole in the first place. Now here are some two further theorems from general relativity and quantum mechanics. In quantum mechanics, every state, it's a theorem, that every possible state that you have, every unique state, has a unique energy or mass up to the symmetries in the problem. We're going to ignore the symmetries for now. Okay? So that means every state in the system has a unique mass. Now here's a theorem from general relativity. The energy or mass of a system can always be measured from far away by testing how much space warps as you approach the system. In fact, that's the qualified general relativist measures mass in this way. You have a thing over there, you walk towards it, and you ask how much the warping of space changes, and that tells you how much mass is there. So that's what you're supposed to do. So now I'm going to say, put these two statements together and come to the following conclusion. Suppose you have quantum mechanics and general relativity. Every state of the system, including the black hole, has some unique mass up to symmetries. And then you measure the mass very carefully from outside the black hole, and you uniquely determine its state. So what's with the information loss? The information is never erased. How can it possibly go away? That seems like a very good argument, but it seems too easy. Why was there such a head-scratching paradox? Here's why. So let's ask ourselves, well, that's very nice. So you can measure the mass to measure the very carefully, and you would know the state of the black hole. You could avoid these paradoxes. But precisely how well do you have to measure the mass in order to be able to get around the supposed paradox? So we already said that Hawking, Bekenstein, and company argued that the entropy of a black hole is proportional to the area of the black hole. There's actually also constants, Newton's constant and Planck's constant and other things. So what that means is that there's a very large entropy. Okay? So according to the standard rules of physics, if you have so much entropy, it means that the number of states that you're talking about is exponential in the entropy. That's what it means to have an entropy. There's lots and lots of different microscopic configurations that look similar. That's what it means to have an entropy. So now let's suppose that you are capable of making a measurement of the mass of the system with a precision delta m, some tiny precision. Then the statement that the black hole has this entropy means that between the mass m and the slightly different mass delta m, that's the resolution of your measuring device, you need to have exponentially many states of the system. But that means to space out so many states, their spacing, their separation energy must be tiny. I'm packing so many different states within such a small range, they must have a very tiny spacing. Now we can put in another theorem from quantum mechanics. It's called the time energy uncertainty principle. Remember, you will have all heard that in quantum mechanics there are these uncertainty principles between, there's been energy and time, momentum and space and things like this. And the time energy uncertainty principle says that if you wish to measure energy with the precision delta E, then the amount of time it takes, delta T, that's the amount of time to make this measurement, is related inversely to the energy precision. So what that means here is the amount of time you need goes exponentially in the area of the black hole divided by constants like Planck's constant. So that was a somewhat technical argument, but the reason I gave it is, this is just a little bit of algebra. But what it immediately tells you is that in order to make a measurement of the mass of a black hole with the precision required to tell precisely what its microstate is, you would need longer than the age of the universe. So that's why this is hard. If we did any kind of approximation, so I have a real device, I'm going to sit there for 3 years and make a measurement, it's just not going to work. It's going to be hopelessly inadequate. So it would appear that what's really going on here is that the information is there about the black hole, but it's very difficult to decode. In this language, it takes a long time to decode. There's something about it that's very complicated, very complex, and hard to decode because of that. So let's think about that. So to do that, to think about that in a concrete way, you need some way of thinking about what are the actual physical states of the system. How do you construct the microstates of a black hole? So I'm actually going to give you the sort of two-slide introduction to decades of string theory here. Okay, so we want to construct now the quantum states of a black hole. And I'm actually going to do this. This is only for the technical my brethren in the field, so they don't complain to me afterwards. We're going to do this actually, strictly speaking, in a universe with a negative vacuum energy as opposed to a positive vacuum energy as it is in our world. That's a technical simplification that helps my colleagues. I'm saying this so that Matt here doesn't complain to me afterwards. But you don't need to know that. Anyway, we're going to construct the quantum states of black holes. So the way in which physicists think about this kind of thing is they often resort to kind of atomic method of building things. You imagine there's a big thing you want to make, and you make the big thing out of lots of small things. You put the small things together. That's the basic method in the construction of states in any kind of physical theory. So in this way, the way you talk is you say, there is a lowest energy state. It's called a vacuum. I'm going to here label it vac in that way. And if you're talking about a quantum theory of gravity, the vacuum is just the empty space, the empty geometry of space. There's nothing in it, right? Just completely flat, it's smooth, there's nothing in it. So the way you work is if you wanted to create states of the system, you need to create little ripples in it. So each little ripple, each kind of ripple, is given a name, and there's an alphabet, if you like, of little ripples that you can make. I'm going to call them x1, x2, x3, etc. So the method used in a lot of physics to describe the states of physical systems is you say that there's some finite alphabet of things you can do, things you can add to the system. It's like adding atoms to the system. So you take the vacuum and you add an x2 to it, then you add an x4 to it, then you add an x1 to it, or you may do an x2, x3, whatever you want, really, right? And this is the way of making all the states of a system. So it's like creating, we can now think more like a computer scientist or an information theorist or something, and recognize that this is like taking an alphabet. Here are all of these elementary excitations, elementary particles, or elementary ripples you can add to space and time. And what you're doing is you're creating very long words from the alphabet. And in this kind of description, the energy or the mass of the state basically increases with the number of letters you add to the alphabet. There was a question there. Right. So it doesn't necessarily have to be in all cases, but in the cases that we're thinking of here, there is a finite alphabet of this kind. So in all the physical theories we're thinking about, there are a finite set of fields, as they're called, or a finite set of objects of that kind, from which you construct longer things. You can make an infinite tower of possible kinds of excitations or things in the world, but you make them out of a finite vocabulary. Yeah. So I'm going to argue from just that fact that almost all black hole states are insanely complex. And we can do that like this. In this language, to make a black hole state, you need to use a very long word built from your alphabet. So it's x3, x1, x4, very long word. To have it have the necessary mass, the number of letters n in the word you have to construct, which is describing the sort of patterned excitations you're putting in the world, must be proportional to the mass of the black hole. So it's much, much bigger than the alphabet size. Now you can resort to a theorem from information theory. The theorem says that almost all long words built out of a finite alphabet live in a certain typical set of statistically random strings of letters. There's a concrete mathematical version of that. You say let p of x be a probability of a random letter in a string. Let q of x be sort of the random distribution. Then there's a theorem by Sanov that says you see the spirit of the thing. You can quantify that if you make very long words out of a finite alphabet, then overwhelmingly many of these very long words look statistically random. In other words, most of the states that you could construct to describe a black hole microstate, most of the things you could do to describe the microstate of a black hole, are in this sense algorithmically complex. There is no short rule, algorithmic rule, for generating any of these states. There's no way to compress it to a shorter description. It is just statistically random. So perhaps you might wonder that this kind of crazy complexity of the microstates of the black hole is the reason why it's also hard to decode, right? Because there's no way of finding a simple rule that tells you what it is. So let's probe that further. And indeed, probing this further has been one of the things that the IT from Qubit collaboration that we're in the Simons Foundation, has been doing a lot over the last few years. So let's talk about what does complexity in this sense mean. So I'm throwing about the word, this is a complex microstate, this is complex, that is complex. But the field that's really studied the notion of complexity most carefully is computer science. So going back decades, there is the sort of parent definition for many of the definitions of complexity, which is due to Kolmogorov, great Soviet mathematician. And he basically said that the complexity of a string, the kind of thing we're talking about right now, right? This long string built out of a finite alphabet, the complexity of a string of letters is the length of the shortest program that can generate it. That was Kolmogorov's definition. Later on, in information theory, Jorma Rissanen had a related definition, saying that the complexity of a string is the length of the shortest code for transmitting it. So that's like taking an image, converting it into a JPEG, which is definitely smaller than the original image, and then sending that, right? It's the best, shortest code you can get. So the more you can compress it, the less complex it is. Then when people are actually building computers, either classical computers or quantum computers, there's a related notion of circuit complexity, which says that the complexity of a computation counts the number of elementary operations or gates you need in the system to carry out the computation. So let's take the spirit of these three definitions and apply them to physics. You might suppose that any sequence of physical operations on a system is a computation, and that things that require lots of physical operations are somehow more complex. I'd like to think about this spirit of things and apply it to the thinking we just did about black holes, their microstates, and why they're hard to decode. So first, I'd like to argue to you that it's a fact that simple initial states, I'm here thinking of elephants and dictionaries as simple states of matter that are sort of very organized, can in fact evolve into black holes. We've already seen that, of course. We've seen that black holes are the universal endpoint of gravitational collapse. So it's true, clearly, that given that the black hole microstates are algorithmically complex, and given that the initial states aren't, they're structured things like elephants, it seems to be the case that algorithmically simple initial states can in fact evolve into complex black hole microstates, and entropy should seem to increase. So you could ask how this happens. How can this happen in quantum theories? So there's been a lot of work on that in the last few years. And the kind of picture you develop is the following. So you start out with an initially organized state, quantum state. But it has a complicated dynamics. The complicated dynamics causes all the elementary constituents of your quantum system to zip around like crazy. And they interact. And they develop a property called entanglement between each other. I will tell you more about entanglement in a minute. But for the moment, you should think about it as a spooky property that causes individual pieces of a system to be sort of tied up with each other, correlated in a kind of quantum mechanical way. I'll tell you more about that in a minute. Right? So this can happen. So if you do that, and then you view a subsystem there, so suppose you look at a part of the system. So the black hole has become very entangled, let's say, and look at a piece of it. Turns out that that little piece will look as though it's statistically distributed and random. So the idea here is that the way in which the dynamics producing black hole microstates produces this complexity is that it leverages standard things that must be happening in quantum physics, in which the dynamics of a system can cause it to evolve from simple states into very, very complicated states that are entangled quantumly in a complicated way. Again, I'll tell you more about what quantum entanglement is in a minute. So how can this happen? So in the study of, not black holes, but regular matter, people have thought a lot about the notion of what's called chaos, statistical of chaos. And chaos is a kind of dynamics that takes simple initial states and makes them very complicated. Let me tell you how this happens. So there are many systems, both classical and quantum mechanical, which are very, very sensitive to their initial conditions. So that, for example, the weather is one such example. Small perturbations in a system can lead to very large changes much later on in the weather patterns, things of that kind. Right? So in quantum mechanics, chaos in a dynamical system has been shown, at least in some systems, or in those that we can control, to sort of scramble information in a certain way. Let me show you how that works. So imagine you have a number of sites like this. Then what happens is that if you've got a complicated dynamics like this stuff bouncing around like crazy, the local information that's stored, let's say in this red arrow, can spread out and become delocalized across many arrows over there. And then this blue arrow can spread out. The information stored there can spread out over there. They all become entangled and correlated across long distances. And in this way, it becomes non-locally organized. Stuff that was originally kind of locally organized. We think about simple states as things that are locally organized. There's a thing here, there's a thing here, and I can understand the system separately by looking at the thing here and the thing there. So what happens in these kinds of very complicated chaotic dynamics is the information that was originally locally organized in the system, to make it simple, gets spread out and entangled between many pieces so that you can no longer tell what the original system was or how it was organized without simultaneously querying many pieces of the later system. So basically, the information that was stored in individual parties early on becomes kind of shared as a shared secret, if you like, between many parties later on. So it becomes inherently delocalized. Obviously, that feels much more complicated. So in other words, multi-party shared information grows over time, and in this way, the complexity of states grows over time. So over the last 5 years, I guess, there's been an enormous effort to try to quantify this kind of thing very carefully and relate it back to the dynamics of the underlying formation of the microstates of black holes. So the kind of way people have been thinking is as follows. So in the traditional field of computational complexity theory, the way people think about this kind of thing is they say, well, I want a certain time evolution in my quantum computer. So I start with a bunch of bits organized on these wires. And then what do? I start acting on them with various kinds of computational gates. So in the language of quantum computers, in a physical quantum computer, that would be like having lasers that act on multiple quantum bits on multiple quantum bits at the same time to change them in some way to a computation. So then you ask yourself, how hard is it to do these operations? And a hard operation, for example, acts on many of these bits at the same time. An easy operation maybe acts on 1 or maybe 2 bits at the same time, acts on a small number of bits at the same time. So what you do in computational complexity theory is you ask, here's the computation I want to do. Here's the initial state that I put into my quantum computer. The computation involves producing a different state in the system after some time, and you ask yourself how difficult that is to do. How many operations should you do? How should you organize them, and so on. So lately, I think in physics, we've been thinking about time evolution, the evolution in time in physical systems also as a computation. Why? There's an initial state, and it evolves in time. So you could imagine sort of how many operations does it take, and what kind of operations do you need to start from the initial state to the final state. So in physics and quantum mechanics, you usually say that a quantum state must evolve over time by something called a unitary transformation. That simply means it's a transformation that preserves probability, and the laws of dynamics of quantum mechanics tell you how that works. So what people have been doing is you can convert that kind of problem into a problem in geometry where you consider this time evolution in a physical system as a kind of geometric motion in the space of possible transformations you can do to quantum states. So it's a bit abstract, but you sort of geometrize the problem, because if you turn it into geometry, there are lots of tools you have for solving that problem. And there has been a lot of progress in trying to understand whether or not, how complex is the time evolution of this physical system versus that physical system versus this chaotic system. If this is the time evolution that's being prescribed by the physical dynamics, are there any shortcuts? Are there any shorter paths? Things of this kind. So people have made a lot of progress. So what progress have they made with regard to the black hole problem? So to explain the physics of black holes and why you get this enormously complex microstates developing as the thing collapses, you need to have an effect where the complexity of the underlying quantum state grows linearly for an exponential amount of time. That's because, in the end, the thing needs to be exponentially complex. It has to be very, very complicated. So a series of investigations have showed a bunch of things, such as, for example, if the quantum states of a system have the property that you can't transform one to the other by using simple operations, then you're guaranteed that this kind of complexity grows in time for a very long time. And by using various kinds of simple versions of the black hole formation problem, people have shown, we have shown, that it is the case, it is likely the case, that simple initial states in systems that can form black holes can indeed evolve into the kind of very complex systems necessary to describe black hole microstates. Okay. So what have we said so far? I'm going to summarize, because this was fairly technical in the last few slides. By the way, when I give these sort of public lectures, I like to give some of the technicalities. And there is a reason for that. Because sometimes when I listen to public lectures, I have the feeling that it's all poetry. But it isn't all poetry. But there are actually concrete calculations behind many of these things. And I think it's important to know that. Right? It's not just imagining that you can do these things. You can do these things. So anyway, let me summarize, because some of that would have surely passed by part of the audience, but not all the audience, given this audience. So far, what have we said? We've said that black holes trap information. We've said that Hawking radiation seems to erase information. But then I said, but you can read the state of a black hole from infinity if you have enough time, so information cannot be erased. So how are these two statements consistent? So the proposed resolution is that the states of black holes are algorithmically complex. And I tried to argue to you that there is evidence that has been developing over the last, let's say, decade. So this is all very new work, that the underlying dynamics producing these states is chaotic, and thus increases the complexity of the states for an exponentially long time, thus delivering these very, very complicated internal states that become hard to decode. That's what I said. So the bottom line from that is, here's this picture of the black hole. The bottom line is that the apparent causal disconnection of the black hole interior from the rest of the universe is kind of a classical artifact of the algorithmic complexity of the state. It's just that any sort of normal observer can't do anything about it. And so it looks as though it just isn't there, right? You can't touch it. Right? But that's just because it's just too complicated to do anything with. Okay, but there's still an issue, at least for me. In all of this, we said when we started talking about Hawking radiation, on the one hand, I said it's all very random and very complicated, but the way I described it was actually pretty simple. I said that it looks like thermal radiation. What is thermal radiation? You can heat up a lump of coal and get thermal radiation. I'm radiating thermally, right? I'm putting out a bunch of photons that go off at my body temperature. That all looks pretty simple to me, right? You may say it's random, but just a photon going there and a photon going there and a photon going there. They're all well separated. They're not actually talking to each other much. I should be able to collect them. And there is supposed to be a promise in classical physics that if I took a lump of coal and I burned it, and I collected every photon that came out and every bit of gas, then I could run the laws of physics backward and reconstruct the coal. That should be there. So there's something crazy here that the Hawking radiation actually looks pretty simple. So where and how is this thing that's supposed to be algorithmically complex stored in the Hawking radiation? Let's talk about that. To talk about that, I need to talk a little bit about what information is, because we want to ask where the information is stored in the radiation. Let's just be precise about the kinds of things we need to do. So first, let's talk about classical information, because it's sort of more familiar. And this is the way it goes. So suppose you have system A and system B. And I set it up so that if system A points up, then so does system B. And if system A points down, system B points down. So in this setup, system A contains information about system B. Why? Because if I measure A, it tells you what B is. That's the way I set it up. That's why A is informative about B. You could make this a little bit more subtle. Instead of making this precise, you could say, well, there's a 45% probability that A is up and a 0.5%, and you can set up a probability matrix like this. There's a 50% this way, 45% this way, things like this. And then basically, you could put up a correlation between A and B. And so information in the classical sense used by the phone company and used by Shannon, using Claude Shannon's method of quantifying information. Anyway, whatever they use in the phone company and what Comcast bills you for, it's just a way of quantifying this kind of correlation. It's a way of giving it a number. So in that language, saying that A contains n bits of information about B means that measuring A allows us to distinguish between 2 to the n possible configurations of B. That's the meaning of saying you've got n bits of information. So that's the classical statement. So everything we've talked about regarding Hawking radiation, black holes is quantum mechanical. So and I want to know, how does the quantum radiation contain information about the black hole interior? So I need to have a notion of quantum information. This is slightly more subtle. That is because quantum systems, unlike classical ones, can be in a superposition of states. Most people in this audience have heard about that before, but that's like this. Earlier, in the classical system, I said the system A could either be up or it could be down, but the quantum system could be a superposition of up and down, which means it's both at the same time in some crazy manner that's hard to visualize. Furthermore, there's a statement that if you measure the state, you go look at it, it collapses. It either becomes up or it becomes down. From then on, it's either up or down. Why or wherefore this happens in the universe, God alone knows. But that's the way it is, apparently. So now we can set up something called entanglement. Because of this superposition type property, there's a new kind of correlation in quantum mechanics that's absent in classical physics, which is called entanglement. So the way this goes is, look at this. You can put a superposition of 2 states of systems A and B. So the A and B can be up and up or down and down with equal probability, and they're kind of superposed. They're both at the same time. So that's called entanglement. And here too, because A is entangled with system B, if you measure A, you can collapse B, right? B can be, at the next star over. It can be an Alpha Centauri. But if B is entangled with A, if you measure A, it collapses A. But because it's entangled with B, it's collapsed to B too. Very strange. So entanglement also means that if you measure A, it tells you about B. One more thing that has a bearing on some of the things we said earlier is that suppose A and B are entangled in that way. In other words, they're up, up, plus down, down. In other words, they're sort of correlated in a kind of entangled kind of way. Suppose you say that you will only measure A. You don't intend to measure B ever. Then you have to sum over all the possibilities of the ways B could be, because you don't know, and they're entangled with each other. You don't know what B is doing. So because of that, if you do that, if you never measure B, it turns out it leaves the system A in what's called a mixed state, which is classically uncertain. So this is a way in which classical uncertainty can be produced in part of a system because it's quantumly entangled with something else, which you're choosing not to measure. And there are various quantities called the entanglement entropy, there's that word entropy again, that quantifies this kind of uncertainty that arises because you're actually entangled with something else. There's something else called the mutual information that tells you how much information in this sense one thing can tell you about the other. So that's quantum information. So the current working hypothesis that I think most of us in the field follow is that the way in which you get back the information about the inside of the black hole from the apparently thermal Hawking radiation is because the emitted radiation and the internal microstates are quantum mechanically entangled in this sense. When you make this stuff, it entangles the inside and the outside. And so by what I just said, on very general grounds, measuring the radiation gives you information about the microstate. Actually, it tells you more. So the general theory of quantum communication is exceedingly powerful and immediately predicts a whole series of things. It predicts that the identity of the microstate will be concealed completely from outside observers until about the halfway point of evaporation. That's a theorem about the way in which you can get information from these kinds of systems. There's a second theorem that after that point, the information is very rapidly recovered. And kind of astonishingly to me, I never thought this could be done. Actually, I didn't think this would get done in my lifetime. In certain simple models of black hole formation, this has been demonstrated in the last few years that this happens. I just find that amazing. So very cool. So it appears, but that's not for astrophysical black holes of the kind that form in the world. These are for simpler toy models of the formation of black holes. So there's still work to be done. But the fact that there is an avenue for doing this, I find amazing. But actually, there's an even more radical thing that this suggests. So what I just told you is the following. I said, here's the inside of the black hole. It has this very complicated internal state or structure. And far away, there are these particles of the Hawking radiation which have gone every which way into the distant universe. And I've told you that they are entangled. And somehow doing that is going to give me information about the inside from the outside. So these theorems in quantum communications theory tell you that after enough radiation has been emitted, the particles in the radiation basically contain an encrypted image of the state remaining in the interior. That's what they're supposed to tell you. But any such encoding is basically a copy of the interior state. It's a copy because, well, it may be rotated and changed in some funky way, but it's the same thing, just written in a different way. So it's a copy. But now there's another theorem in quantum mechanics called the quantum no-cloning theorem that says it is not possible to copy a quantum state. So again, we seem to have a problem. What the hell? Right? So there's a proposed resolution to this. And the proposed resolution is after you wait long enough and enough of this radiation comes out, some part of the interior of the system, the inside of the black hole, and some part of the radiation are the same thing, even though they're sufficiently far apart. Not that they look the same thing or one encodes the other, but they are the same thing, right? Think about how crazy a statement that is, right? It says that acting on the radiation with the correct sort of operations far away will modify the interior of some very distant region. So you might say, well, that is crazy. Ain't so. And it certainly seems to contradict all of our experience with the local and causal nature of physical interactions. But a lesson we keep learning in physics again and again and again is that we have certain experiences of the world up to some length scale, up to some size, up to some biggest size, up to some smallest size, up to some time. There's some range over which we make our measurements. And then we make a theory of physics that fits that data really well. And then we trust that if we extrapolate that beyond the regime where we measured it, we should be okay, at least for some distance. And again, we find that that's not true. Right? When, at the turn of the 20th century, people were able to make measurements at sufficiently small scales, they discovered that, well, the world is really quantum. It's insane. right, is kind of crazy. And if you measure the world at sufficiently long distances, well, Newton's laws are wrong, right? It's actually general relativity, right? So we keep discovering this again and again, that if you extrapolate the laws from what you saw, eventually they won't be true. There's something wrong with them. So I'd like to tell you that this idea that you might be able to influence a distant region by touching this faraway part of the radiation isn't actually inconsistent. The reason is, the interior of the black hole, as represented in the Hawking radiation, is represented in a very complex pseudo-random looking code. So that's also a recent demonstration that people have made. This code has a property called error correction, which means that the way in which this information is embedded in this radiation is that any reasonably local action, you move a couple of the photons around, you bounce it off something, stuff like that. Just any reasonably local action of physical things in the radiation do not affect the encoding. It's an error-correcting encoding. And as a result, if you want to do such an acausal remote action in the interior, you are going to have to do actions that are algorithmically complex. That's something I'll talk about tomorrow in our technical talk. Right? And such algorithmically complex operations are computationally impossible for any reasonable observer. So what I'm trying to say is it's actually possible that the physical principles of locality, that is, you can only affect neighboring things, and causality, that you can affect a distant thing, you have to send a message to it, which takes a certain amount of time. But it could be that these things are wrong in detail. That fundamentally, physics looks causal in this way just because you can't do very complex things. It can happen here. It can be consistent. That the reason why we haven't seen crazy stuff like that happen is we haven't, and maybe we can't, do sufficiently complex operations. Maybe the universe can, but we can't because it's algorithmically complex. So this is, I think, this body of ideas which has been emerging over the last decade is just a really beautiful coming together of ideas from quantum mechanics and general relativity and computer science. These are all ideas that have come from and information theory. And I hope many more wonders will come out of it. So I'm going to stop there.